I know. And I appreciate you realizing I did it to myself, so oh well, too bad for me. But I do that a lot because that's what stats is. I don't want, part of statistics is actually taking random samples.
Yeah.
So there will be some take-home stuff, some other stuff where you guys have to actually take random samples. So I did take off a few points on a few people who obviously did not do it randomly.
Oh, come on, man.
You could argue with me.
You
can
could
come up-
randomly get the tops, actually.
Huh?
Yeah.
Give me 1 point.
For what?
I randomly selected the top 10.
I do find that hard to believe, but it's possible. Probably so small that I feel better taking a point off for you.
Ah, come on.
So that's too bad. All right.
You said standard deviation over average?
Yes. All right, guys. Any other questions from up 333?
Nobody else would do it. I threw in some nice numbers.
Okay.
I did. Descending order too. I didn't even mix them up.
You're supposed to mix it, silly.
Okay.
Data on the board.
Yeah. So let me just ask you directly. Looking at these, there are 10 data points up on the board. Let's say this is the grade on a 50-point quiz in some class. Right? Don't want to be this. But what would you say? What would your guess be for the 80th percentile?
45.
Which we'll designate as P80.
47.
All right, I got a guess there. 47. Any other guesses?
45.
45. Any other guesses? Why does 47 make sense? Why did you say that?
Because there's 20% above it.
Cool, I like it. So to be now, so one thing I'm asking is, do you understand what the hell that might mean? And if you've taken the SAT, percentiles is how they give you your results. And the reason they do that is because the SAT changes each time they give it. So randomly it could be harder at one point than it was some other day. So what they do is they compare how you did with everybody else who took that test on that day. And they rank you percentile-wise as far as if I'm in the 80th percentile, how many people did worse than me? 80%. So how many people did better than me? 20%. So I love the reasoning. And I could be really mean and say, even though you're wrong, but it's a perfect reasoning. There's 20% of the data above. But how much data is below 47?
7.
1, 2, 3, 4, 5, 6, 7 out of 10 is 70%. Damn. You guys kind of with me here. I want to make sure everybody's kind of with me. This idea is actually really straightforward. It just doesn't quite work exactly the way that we sort of would hope it would.
47.5.
So if you think it's 48, then there's only 10% above.
47.5.
Beautiful. So percentiles are actually a more general thing than median. Sometimes for the median I have to go between two, don't I? Because what's 50% of 4? 2. Is the median the second number though? No. I've got to go in between the second and third, don't I? Yeah.
So the median is the 50th percentile.
The median is the 50th percentile, exactly. Right. A little thing that comes out of this is that the median is also known as P50. Why does it make sense? Because the median is supposed to be right in the middle. So how much should be below it? Half. How much should be above it? Half. Right? Okay. Real quick little caveat here. For very small sample sizes, the percentages really start to not make direct sense. If I have 4 things, can I talk about the 73rd percentile very easily? No. Right? So don't get hung up. We've only got 10 data points up here, so it's not going to be perfect. But this illustrates the point. To find P80, there's a two-step process. All right, can I write? No, Jeff, you can't. To find a percentile 1, what does 80th percentile really mean? How far into the list do you want to go? How far into the list do you want to go to find the 80th percentile? I want to go 80% of the way in, right? So step 1 is take the percentage of n. So in this case, I want to go 80% of 10. That's how deep I want to go into the list, right? Okay. Maybe. Only makes it, I want to get the 50th percentile, I want to go halfway into the list. I want to get the 80th, I want to go way far into the list, 80% of the way into the list. So in this case, what is 80% of 10? 8. So here's the trick. It's sort of related to the n plus 1 over 2 with median. If it comes out to a whole number, you take the average of that one with the next one. If it comes out to a whole number, average 8th and 9th. So the median, I mean which one am I doing? P80 would be the 8th number, 47, plus the 9th number, 48, divided by 2, 47 and a half. Now does 47 and a half do what it's supposed to do? What percentage is above 47 and a half? What percentage of the data is above 47 and a half? 20%. What percentage of the data is below 47 and a half? 80%. There you go. It does exactly what it's supposed to do. How are we doing so far?
So when would you be hitting correct? Like, could you say 79% is 40%?
Here we go. You ready? So in this case, what would let's say P40, P45, 45th percentile. What's the first step to find it?
25 minus 11.
What's the first step to find it? 45% of 10 in this case, right? It's only 10 now because there's 10 data points. It's not 10 always. It's how large your sample is. In this case, it's 10. What's 45% of 10?
4.5.
Yeah, 4.5. If it comes out to a whole number, you average that one with the next. If it comes out to anything else, you round it up to the next number. So the answer here would be the 5th number. The answer is not 5. The answer is the 5th number. So what is the answer in this case?
25.
1, 2, 3, 4, 5, 25. So there's really only two possible outcomes for this word. It either comes out to be a whole number, in which case I average that with the next one, or it comes out to be a decimal, in which case I always round it up. Even if it would have been 4.02, you round it up to the 5th number. So step 1 is where's the answer? Step 2 is go get the freaking answer. My answer is not 5. My answer is not 8. Okay, how are we doing? All right, so real quick little example using the median. If I have I want to find P50. How would I do that for that list there? P50. What's step 1? 50% of 5, good. And what's half of 5? 2.5. It came out to a decimal, so what do I do?
Round up.
Round it up to the 3rd, right? Round it up to the next whole number, 3rd. The 3rd number is the answer, so then step 2. What is the 3rd number? Step? P50 is 4. And like we just said a minute ago, what is P50 also known as? The median. And what is the median of this data? 4. Holy shit. Thank God. All right. So the work here is actually exactly the same work we do for the median. It's just that the median is a lot more specific. You can kind of adjust the rules to be easier for the median because it's a more specific example of a percentile. How do you feel so far? I mean, this math is not very involved. Obviously, what's got to be true about the list to begin with? Got to be in order. Or else you can have the lowest damn test score, but you put yours way up here. I'm in the 100th percentile. Damn, no, you're not. It's too bad. Okay. So, what I'm going to do, I'm going to let you guys look at this list of data. Try to get a few percentiles. Thankfully, I've already put it in order for you. There are 49 data points I'm going to put up here. Yay! Someday. Hey, Beck, could you do the one that says whiteboard? Might be good enough. Let's see. Oh, yes. Can you guys see that okay? Notice how it's in order? Right? Okay. 7 by 7 grid. I want you to find these things. Find P25, P70, P11, and P50. Yeah. Remember, I told you this list. There's 49 data points up there. 49. That is important. 49 data points.
Are they in order?
They are. Please realize they're in order as you go up and down the column. Not by moves. Call me over if you need some help. Just make sure we're on the right track. Step 1 here would be to take what?
25%.
Good, 25% of
49.
49.
Which is 12.25.
12.25?
Just 50.
So you round it to
13.
13, always up. Right? So the 13th number is the answer, so step 2 is go get the freaking answer.
68.
So count to the 1368.
Yep.
Okay. So hopefully you got that. If you did, you're on the right track.
On the test, we have to show step 1, step 2.
Yeah. You have to show me your work always. You don't have to label them step 1, step 2.
Well, that's what I meant.
Good. Yeah, you, whatever you end up, don't worry about repeats. Don't worry about repeats. So I think what he's getting is for P, what was it? 50. You get an 83. Don't worry that there's several 83s. There's actually some disagreement with that, depending on which book you get or which teacher you have. I say screw it. They're all valid data points, each one of them. So wherever you land is what you do.
That's right.
How are we doing so far? What do you guys get for P70?
88.
88? Because you did 70% of 49. You got 34 something or other. I don't know.
34.3.
All right, and then you went out, rounded that up, and then went to that number. What about P11?
61.
61. And P50?
83.
83. Cool. So we already know another name for P50. There's actually even another name for it. What do you think another name for P25 would be? Yeah, which quartile? First one. 1/4 of the way through would be 25%. So another name for P25 is Q1. That's creative. What about P50 then is also known as
Q2.
Q2. So what would Q3 be?
75.
75%, yeah. Good. Q0 and Q4, you don't see that very much, but Q0 is the lowest data point. Q4 would be the highest data point. It's like your bookends, the range, right? Low and the high. Cool. All right. It's not too bad, right? Pretty straightforward math. So here's how that connects to what's called a box and whisker. I know. The box and whisker plot. Not my wording, by the way. It's not something I made up. Uses what's called the 5-number summary. Five-number summary is low, Q1, Q2, Q3, high. That kind of makes sense. It summarizes my data. What's the lowest? What are the 3/4 in the middle? And what's the highest? Kind of gives me an idea of how spread out it is. It gives me an idea of where it's grouping together, all this kind of stuff. So the lowest one from here was 42. The highest one was 97. We already did which ones of these? Q1 was 68. Q2 was 83. Now here's the funny thing. Go back to your P25 work. What did you guys get when you did 25%? 13, right?
Yep.
If I step 13 from the bottom in to get to Q1, I step 13 in from here to get to Q3. Does that make sense? If not, it's okay.
Say it again.
What?
I'll say it again. So when you take 25% of 49, you round it up to 13, right? So then I take 13 steps in from the bottom. To get to Q3, I take 13 steps in from the top.
Okay.
Maybe. Now if you don't like that, what's 75%? To get Q3, that's P75. What is 75% of 49? 37? So did you get, what is 75%?
That's rounded up.
Let's round it up
From
already.
36 point.
Gotcha. So 37, you can count all 37, 37, but I'd rather just count 13 in from the bottom. It's the same number.
So what do you mean we can
89.
just keep adding
89.
15 numbers when we have a P25? We can add 13 number, that's gonna be P50, and then adding 50, 13 is gonna be P75.
I like it, because what was this one? Half of 49. We got to be careful though, because we rounded that number, so you got to be careful about the 13 everywhere. Yeah. But my point is, if you don't quite get that point, you can always just do P75 all the way. Take 75% of the list and then go that far in. Some of you guys might realize it's a nice shortcut to get to Q1 and go the same amount in to get to Q3 just from the other side. It'll make some of these problems a little quicker, a little tiny bit quicker. Here's my 5-number summary. Here's how you make this into a box and whisker plot. Somebody give me an idea of a scale so I can fit all these data points on it. Where do I want to start maybe and end? It's a nice scale.
40 to 100.
40 to 100. Sounds good. Let me not do that. So 50. Let's go by 10. That sounds about right. So make that for yourselves. Box and whisker is stupid easy. The math here was not terribly involved. The funny thing is, I'll say this right now, if you were to put all this data into your calculator, and remember 1var stats, stat, calc, 1var stats, if you scroll all the way down, the last 5 things it tells you is this. So you still have to show me the work. You should know that about me by now. But you can certainly check your work right there. So when you do 1var stats, you scroll down, the last 5 things it tells you, min, Q1, median, Q3, max. Bam. So here's how you make a box and whisker. 42 is about right there. So you put a line right over 42. Keep going. 68, line, 83, line. Sounds like I'm an actor. 89 is about right there, 97. Okay. Right? Not too bad. Box off the middle Q1, Q2, Q3 like this. Here's Q1, Q2, Q3. There's your box. And there's your whiskers. Yeah. Can you guys see how to make that? It's not that bad. We'll box off the middle 3 lines, whiskers out to the last 2 lines, right outside. It gives me an idea of spread. It gives me an idea of where things cluster. Very quick. Can anybody tell me what percentage is in here? Always. What percentage of the data of the what percentage of the data is in that box?
68.
Always.
No?
No. Did I say anything about this being a normal distribution? Is this a normal distribution? No.
No.
Shit.
It was a good try, though. I like it. Think about it. What was this again? What's that? That was Q3, right? What percentage is below Q3? 75. And what was this line? Q1. What percentage is below Q1? 25. So what percentage is in between? 50. Cool. That box is always the middle 50%.
Always.
And very often, if you look at the Princeton book of colleges, if you think about transferring to a college somewhere, very often they have like the middle 50% of SAT scores, or the middle 50% of ACT, or whatever. They like that middle 50% because it gives you a very quick idea of no outliers, just what's the meat of your student body. Where are they? The middle 50%, where are they? Yeah.
Do you have to have that lower line with intervals, or can you just do the minimum maximum value as actual end whiskers? Because like the book, there's no lower line of value, so
I know.
there's just
So be careful about the book. They use computer software to create theirs. So they don't have to rely on a scale like us humans do. You better set up your scale.
Yeah.
Otherwise, every box and whisker ends up looking like this. You know, like perfect. And it really shouldn't look that way. So your scale...
But so if we're doing it for you, though, do you always want that scale?
Oh, yeah. Yeah. Because otherwise you just kind of put and you're not being extra careful that the scale is actually being consistent. They don't have to be because the computer makes it for them. Ooh. We don't have that little
In my
computer.
homework, I just kind of eyeballed it. So
Oh, really?
try to make it
All right.
scale, but
I'm with you. I understand. Yeah.
So that would be right slanted, pretty much a graph.
Yeah, that would be, actually that would be sort of to the left. That'd be the tail to the left.
The tails to the
Yeah. So here, real quick. These values we're using, by the way, were the grades on the test. So I made 2 box plots. That's this year, and that's last year. Very quick glance, and they look the same, right? The little difference is ours is shifted down just a little tiny bit. Not the middle is almost in the same place. But last year I had, somebody crazy good. He actually had already taken calculus, so he got 106 on the first test. So it kind of skewed everything a little bit. And this year I got somebody take just a little bit lower, but basically they're in the same place almost. Which as a teacher, it doesn't have to happen, but it makes me feel like, okay, I got about the same distribution of students and backgrounds maybe and stuff. If it was radically different, I'd be like, holy crap, did I not teach something the same way? Did I make my tests different? That's the kind of thing I would look at as a teacher. What did I do to cause that, or is it not me? Was it just the randomness of students coming in, and they were all either much better or much worse? Yeah.
Do you keep box plots for all your classes?
Do I? No, not all the time. Sometimes I do. Especially when I make a big change. On the first test, I make a box plot compared to last year. I didn't really make a change, but I just did this just to show you. This is what I expected, because I didn't make a change. The test was basically the same as last year. I just changed some of the numbers, but they're the same format. So this is what I expected. This is what happened. I like it. Okay, cool. You guys kind of get a feel for that? What's that?
The student last year were better than us.
A little bit. And plus I had a couple, he wasn't the only one that had already taken calculus. So I had a couple of people that signed up just so they could take stats, and they're going to get it a little quicker. So now section 3.4 is officially due. For those of you doing the online homework, by the way, in case you didn't get that note from me, I did extend the deadline a little bit for chapter 3 since I extended the deadline for everybody else. I figure I should do it for you guys. Yeah.
I feel that
I think that if people had a better understanding of statistics, period,
it's better for you.
a lot of things would be better. Yeah. And that's just one of them. I mean, if you knew how to analyze your own grades, they could tell you something about a change you made or something. I mean, that would be awesome. If you don't have a clue how to analyze it, you just keep on going forward. There's not too much to inform you as to the outcomes of what you're doing. I think that's it for this. Yes, cool. All right, love it. So any questions on that section 3.4? That one's pretty straightforward, I think. Let me ask you this. Now, this is what I've been sort of desperately waiting for. Everybody take out a piece of paper. Pop quiz, no. Take out a piece of paper. And what I want you to write really big is the day you were born. Not Monday, Tuesday, but like I was born on the 21st, so I put 2-1. Right? So the day you were born. If you were born March 7th, you put 7. You with me? Put the number of the day that you were born. Really big, so I can see it when you hold it up for me. You have to.
Just the date.
Don't do it. What's that? Just the number of the day, that's it. Don't put March, don't put April, just put, if you're born September 30th, you put 3-0. That's it. Let me do it too. There. So there, that's me. All right, so.
I'm ahead of you.
Here's the thing. We're about to get into the section of probability. This is a very interesting example of probability at work. Where are my January babies? All right. Hold up your papers. So you got 21, 29, 19. Are you January? No. No, okay. 21, 29, 1, 7. So what I'm doing is the probability that somebody in here shares a birthday with somebody else is higher than you think. Now think about it. What do you think? Do you think somebody in here has the same birthday as somebody else?
Yeah.
Now it's because of the way I said it. Whenever somebody hears something like that, they think, it's very unlikely somebody else has my birthday. But that's not the question. Are there two people in here who share a birthday? That is a much higher probability than you think.
Be even higher probability. There were 367 people.
But it doesn't even take that to tell you honestly. Obviously, then you'd get a good chance, right? In fact, you'd have to have it. Once you get about 30 people in a room, there's a better than half chance that there will be two people that have the same birthday. So let's keep going. Let's see if this works. Last year I actually talked about putting money down on it, but sometimes I'm not going to put any money. February babies, hold up yours. 18, 12, 5, 7. All right, so no February. What about March? By the way, happy belated. March 1916. What about April? 12-12 right there. 1919. What's the probability of that? So 12-12 right there. See, now that's crazy. You guys get what I'm saying? I mean, there were two sets. In fact, we haven't even gotten through the whole year. Last year I had to go to October, I think, before I finally. And everybody's going. That's what I was talking about putting money down on. And I was like, what did I have to say? This happened. That's the quickest. Let's keep going real quick. So where do I go? April, May. Where are my May babies? May 4th. Don't worry. You gotta represent me. June. We got 25, 12, 16, 5, 5. This is probably this is the most I've ever had. July. All right, 18, 12, 11, 17, 4, 31. All right, nice distribution. July, where am I at? August. August, 6th, 1st. I like that the August guys stay together. August, September. 27, 29, 21, 1. Okay. October?
My mother.
Huh?
You, my mother.
I'm your mother? No, you and your mother. Remember, October 1st, right here. 1st. How many is that? Is that 4 pairs?
Yeah.
November. 4th, 1st, 16th, 7th. Okay. December. 2nd, 16th, 26th, 13th. Okay. Didn't leave anybody out. I didn't skip any. All right, cool. Now think about it. That is kind of crazy. That goes against what you would think. Whenever somebody hears that, I think I'm going to put money on. I should have this year. I could have maybe got some. You guys think personally. Nobody else has my birthday, but it's just out of this group of people, do any two of them have the same birthday? So there's a lot more chances than what we think of. We're like, on September 21st, there's not 300 some odd people in here. Nobody else has my birthday, but it's a lot more flexibility. Just any birthday that anybody has, does somebody else have that birthday, right? Here's another misconception we have. Would you ever, in a lottery, like a 4-number lottery, would you ever bet the number 1, 2, 3, 4?
Yes.
Some of us would. Because, if you're going to put money on this stupid game anyway, you might as well bet any freaking number because they all have the same chance. Our brain, though, says, no, something else is going to happen, like 7, 9, 2, 5. That sounds better. That's got a higher probability, but that's because we lump that in with everything else, right? We think 1, 2, 3, 4, 5, 5, 5, 5. That's not going to happen. Something else. So let me pick something else and it's got a higher probability. No, each individual thing has the same probability, right? Okay. So I'm trying to get you guys to understand the unfortunate thing about probability is that our brains are not wired. There's no biological imperative for us to understand probability. So that's why we don't. We mess it up so much. Probabilities, where we should really know them, we don't. And that's what gets us in trouble sometimes. I am a stats teacher that sometimes does, not in a long time though actually, but I used to play the lottery every now and again, just because. You never know.
Have you won anything big?
The very first time my friend and I played when we turned 18, we went to a gas station. He didn't win anything. I won like $21 or something, and I was like, whoa, this is awesome. And I got some more from the winnings there, and I think it was 21. And I never won anything again after that, basically. But thankfully, I don't play like crazy amounts.
Yeah.
I always start to cry on people. I'm like, you should buy bread and milk. Don't buy a lottery ticket. You're not going to win. Just stop it.
Do you believe in the saying that the lottery is attacking people who are bad at math?
Say again?
Stupid people.
Oh, yeah.
It attacks that people who are bad at math.
Unfortunately, in some cases, yes. This is true. Because it's a risk analysis. It's riskier to do that than to go buy yourself things you need to live. Right? Whereas if you got a lot of money, unfortunately, the people that can really play are the people that don't need the money.
Yeah.
Yep.
I won $500
$500.
on a scratcher on my birthday, so you guys can all stop.
You've taken the probability of the room now. I like that's another misconception. If I flipped a coin 100 times, is it impossible for there to be nothing but heads?
No. Nope.
If that did happen, what would I think?
You would think that it probably wouldn't be a heads anymore, but you would have a 50-50 chance.
No, even beyond that, even less than that.
You think that the coin wasn't cheated the same?
Yeah, I think the coin was somehow weighted, right? It would be evidence that the coin was weighted. So a lot of what we're going to do in this chapter 4, we're going to refer back to later because we use probabilities to talk about, is it strong enough evidence to show something? So if I flipped the coin 8 times and I got 8 heads, that'd be a little weird. But I wouldn't go, oh my God, holy shit. If I flipped the coin 1,000 times, number one, my life kind of sucks that I'm doing this. But number two, if I only got heads, then, and I'm really sure it's a fair coin, that'd be like, whoa, this is some major event. And it is, it would be. If it was a fair coin and I flipped 1,000 heads straight, that is crazy improbable. Not impossible, nothing's impossible almost, right? I can flip it 1,000,000 times, get nothing but heads. That's not impossible. So there was a question in section 1-2. It said, is it likely, unlikely, or impossible? And to get 6 jackpots in a row in a casino, you go ding, 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 ding. You can't even do that anymore. Here you go. Hit the stupid button there. And you do 6 of them and you get nothing. You get 6. That's not impossible. That's not impossible. It's not even impossible to do it on the same one. Jackpot. Jackpot. It's not impossible. The people next to you hate you, but it's not impossible. It's entirely possible. Okay. Let's see. So let me just do a little bit out of section 4.2. We'll head out a little bit early. All right. There are 3 main types of probabilities. And 2 of them are linked. The first type is what's called theoretical probabilities. I think the book, I gotta use the same words. Well, they call it the classical approach for some stupid reason. That's the book. This is exactly what it sounds like. What would you say if I flipped a coin, what's the chances I get a head if it's a fair coin?
50%.
Did any of us actually just now flip a coin?
No.
No. We did it theoretically, based on the possible outcomes. Now, one thing I've got to realize is, why did you say 50%? There's 2 sides, but it's more than that. Not just because there's 2 sides. If I said, what's probably it's going to snow today? Would you say it's 50% because it could snow or not?
No.
No, that sounds more like my little brother. My little brother said to me, you teach probabilities, right, Jeff? I'm like, yeah. He said, why do you have to make it so complicated? Either it is or it ain't. 50-50. And I'm like, James, never become a surgeon. What's my chances, Doc? 50-50. So probabilities have their place, obviously. What would you say the probability is going to snow today here?
0.
Yeah, basically 0. Not exactly 0, because you never know what could happen. Climactically, what heck, you can get hit by a meteorite and throw the whole Earth off kilter. So, but it's really stupid close to 0, right? So just because there's 2 outcomes doesn't mean that it's 50-50, obviously. Why is a coin, if it's a fair coin, why is that 50-50?
Has an equal chance.
Because then both sides have an equal chance. Does not have an equal chance to snow or not snow. So theoretical probabilities are based on equally likely outcomes. And what it is, the probability of some event. Why did I say it was 1 out of 2 for a coin? Because there was the number of things I'm looking for divided by the total number of things that can happen. So in this case, there are 2 things that can happen when I flip a coin, heads or tails. And how many of those things am I looking for? In that case, it was a head. So 1 out of 2. Yes, sir.
Can it just land up on its side?
Good, sure. We'll ignore that, the third possibility. What if I roll a die and I'm looking for a number less than 3? What's the probability of that happening, assuming it's a fair die?
2 out of 6.
Yeah, so use this idea. What's the total number of things that could happen? 6. I'm not using a weird Dungeons and Dragons 21-sided thing, so I don't have too many geeks in here. So 6 possible things that could happen, and how many things am I looking for? How many numbers are less than 3? 2. 1 and 2. So 2 out of 6 is a 1/3 chance that I get a number less than 3 when I roll a die. What does that really mean, though? Does that mean every time I roll a die, I'm going to get one number less than 3 every 3 rolls?
No.
So what does that 1/3 mean? What does it really mean?
33% of the time, you're going to get a number less than.
And the big key phrase you used there was of the time. This theoretical probability really only has meaning when it's a large number of times that I'm doing something. Any individual time, anything could happen. But over the long run, it's got to start following these percentages. Yes, sir?
So it means that each time you have a 1 in 3 chance.
Yes, but more specifically, if I roll a die, let's say I roll a die on the same day I flipped that coin 1,000 times. I roll a die 6,000 times. How many times will it come up to a number less than 3?
2,000.
How'd you do that?
Divided by
1/3
3.
times 6,000. 1/3 of the time it will be a number less than 3, and I roll it 6,000 times, so I'd expect 2,000 times to get a 1 or a 2. If I get 1,980 times, is that freaky?
No.
No. If I get 5,900 times,
Yep.
that's freaky, yes. Right? Then I'm worried about my die. Beyond me having the time to do this, I'm worried about my die. It's been weighted. Okay, how are we doing so far? Is that? So on a single instance, if my doctor tells me there's a 90% chance I'll survive the surgery, on that single instance, it doesn't mean a damn thing. What he's trying to say is 90% of all surgeries like this, the patient will survive. 10% they won't. So if they do 100 surgeries, 90 of the patients survive, 10 of them don't. That's what it means. It only makes sense over the long run. So that connects with this idea. I did promise we'd get out of here early. I'm trying to stick to that. What's called empirical probability. And of course the book calls it relative frequency or something stupid. And that's really what it is though, relative frequency, but it's called empirical probability. Empirical means based on observations. So, does everybody have a coin? Can you guys all take out a coin? Whoever has a coin, take it out. True. But let's not do that. I want real physical occurrence.
I have one.
Cool. Everybody has a coin, take one out. If it's a quarter, can you give it to me? No. Change. All right, so everybody flip their coin that's got their coin out. Flip it. Let's all hope nobody loses an eye.
Ah, shit.
Or, all right, how many heads? How many got heads? Raise your hand if you got a head. 1, 2, 3, 4, 5, 6, 7, 8. What's happening? This is weird. Do that again. We're just waiting. If you got a head, raise your hand again. All right. 1, 2, 3, 4, 5, 6, 7. 8. Okay, I got it. So 8 heads. How many got tails? Raise your hand. 1, 2, 3, 4, 5, 6, 7, 8. That's funny. Of course that's funny. So the empirical probability, and actually to tell you honestly, that kind of is weird. Because again, this is a specific instance that it came out to be exactly 50-50. What's more likely is it would come out to be 7-9 or 6-10 or something like that, because there's more options for those. Yeah.
How is that more likely if there's a 50% chance?
This is not there were 16 flips of the coin. So there's a much less than 50% chance to get 8 heads, 8 tails. Much less. And we're going to actually get to the point where we can calculate that. That's why I'm saying it was higher to be something else. What's something else? 7-9, 9-7, 10-6, 6-10, 5-11. There's a lot more options for something else. That's why it's a higher probability for something else. So this is actually a little bit freaky that this happened. But empirical probability would be based on what we actually see. What's the probability of a head? Well, now it's still 8 out of 16, 50%. So I would say probability of a head is 8 out of 16. That's what this symbol means. Probability of a head is 50%. But be careful. Okay, good. So that was a little weird, tiny bit, because it shouldn't necessarily come out to be exactly 50%. But the point is, if I do it for long enough, if I flip it 5,000 times, and I get 2,497 heads, meaning I got 2,503 tails, that would make sense, right? In the long run, the empirical probability has to match up with the theoretical probability. You guys get that? So the link, there's actually a name for this. It's called the law of large numbers. That's the name. It's not my name. The law of large numbers, which means if you do something long enough, the probabilities you observe have got to match up with the theoretical probabilities. If not, your theory's wrong. So this is basically what we use in science. We have a theory, we check it by doing observations, and we go back and say, oh shit, our theory's probably wrong somewhere. Okay, maybe. So for now, that's pretty good. We just barely got into chapter 4. I just want to get a little bit in there. So next time we'll keep going.